Our scaffold has cores that have protonation state challenges with them. So there's isoquinones and other things that if you do not model your interaction with histidines appropriately, and I'm not even sure a single protonation state is appropriate representation, which is what we're stuck with most of the time, of both, and they're coupled, right? So this active site of the cysteine, right, exactly, coupled with cysteine, of course, whose oxidation state may be unknown. So I think that's the challenge for our particular series, because all of our compounds are quite related to that.
Let's think, John Codera, we are running behind. You can turn that. Our next speaker is Michael Schertz. So, your stage, Michael.
Thank you. It's wonderful to be here again. I was on that chain of emails, so this been going since 2010. So this is about 15 years in a free energy meeting. So I'm going to talk about playing Mr. Potato Head with different free energy methods. So the goal really in this is to explore the correlations between two topics of fundamental importance. First, one of the biggest problems of all these things and why we still usually run with really simple force fields is because we still have the multiple timescale problem. They're very fast motions and that we need to simulate in order to get the physics right, but very slow motions, large scale rearrangements, resulting in large free energy barriers between metastable states, causing kinetic bottlenecks. But also, one problem we're dealing with. But one thing we also do is we're running free energy calculations with intermediate lambda states in many of the things we're doing: protein ligand binding, understanding biophysical mechanisms, and other formulation polymorph prediction problems. We're running a lot of these free energy calculations. So how can we take it? How can we use some of these concepts to improve this problem? So there's lots of ways to improve sampling. I'm not going to go over all of them. It's really just a zoo of things. But I want to put forward the Taco Bell formulation of stat-mech methods. That if you go to Taco Bell, there's really only a limited number of ingredients, right? So you've got a certain set of foundational ingredients, and really there's a combinatorial large number of methods you can get by mixing these same ingredients, whether you corn or flour or what you put inside something else. So and we have this in sampling methods: constructing bias on a collective variable, assuming things are Gaussian, integrating out degrees of freedom, interpreting a derivative as an expectation value, accumulating partition functions separately, using importance sampling to calculate unsample averages, introducing dynamics along an auxiliary variable, expressing it as a maximum likelihood problem, machine learning. So there's a lot of different things we can put together in order to the combinations that we can look at. So, how do we make sense of all of these? There's one, I'm not going to go into this hierarchical decomposition, but you can take a look at this LiveComs article trying to break down these different methods. We ended up discovering there were at least 2 or 3 different ways that you needed to branch this out to hierarchically decompose them. But take a look at this and then look at some of the ways we've thought about this. So today I'm not going to cover all these things, but I'm going to explore a few different combinations that we've looked at over the last couple of years. So of course, alchemical intermediate states are necessary simulated intermediates in free energy calculation. If we're doing something like a solvation free energy, a mutation free energy to do some sort of relative binding free energy, and any sort of full free energy calculation, we need to do, in order to calculate the ratio of probabilities and thus the free energy between the two end states, we have simulations and we can describe them with some coupling parameter. If it's a pathway, you can come up with some in functional space, you can come up with a parameter that describes that. The lambda equals 0 equals initial interactions on, final off. Of course, initial and final can be swapped. You have some simulations along this path that interpolates between the end states and a lambda equals 1 final state. So we have this setup. We have this extra dimension that we're simulating along, as well as simulating doing the configurational sampling. So one thing that was noticed a while ago is the dynamics in the alchemical variable can frequently enhance sampling by allowing systems to go around barriers. If you have to simulate this extra degree of freedom itself in the physical problem, why not do some sampling in that variable as well? So if we look at here along this string, we have some collective variable between 2 metastable states. And here In this dimension, we have our alchemical variable. If you look just at the free energy as a function of this collective variable here, there's these minima that it gets stuck in. But very frequently, if you go along the alchemical variable, you'll discover that that barrier disappears. And you can go back, and if you can sample both in the alchemical variable and in your configurations, you can go back and forth quite easily. One example of this is if you've got a ligand at a binding site and your end state is the ligand, pinned by some harmonic potential so it doesn't wander away, but not otherwise not interacting with the system. It can reorient, it can jiggle around, and when you turn the interactions back on, it can find a new binding position. So that's an example of how at different lambda states, the dynamics might be much simpler, and by coupling to that change, then you can improve the sampling. There's a couple different types of sampling you can do in the alchemical dimension. One that we've been playing around a lot is expanded ensemble simulation, where within the same simulation, you can visit different alchemical states. You do MD for a while, then you do a Monte Carlo move, you reduce your Leonard-Jones interaction parameters, keep going, and you carry out this process so it samples over time all of the lambda states and sampling through configuration space. So your probability distribution is proportional to this. Now, one important thing is you can preserve all the individual Boltzmann distributions if you put a configuration dependent weight here. And it turns out you actually need this to do good sampling. You need to adjust the weight, the configuration independent weight for each different alchemical state, because otherwise it spends all its time in the lowest free energy alchemical state. So you have to essentially learn the free energy as you go, approximately. It doesn't need to be exact, but you need to learn it as you go in order to evenly visit all of the lambda states. So pluses and minuses. A Hamiltonian and replica exchange was something people that generally tried earlier, is which you have all of your lambda states. If you're running any free energy calculation, you have a set of these going, but you introduce switches between them that you accept and reject if the energies are compatible with one going up in lambda state and one going down. Using just Metropolis Monte Carlo criteria, and so you carry this about. And so at all times you have one simulation in each lambda state, but they can switch which ones are. So it's the same set of continuous configurations can raise and lower in lambda state, and thus sample and access potentially faster dynamics. Actually, you need to think about this as the probability of the entire system together. It's a product of the Boltzmann weights of all the individual states. And you don't need weights because you enforce that there's at least one visiting each lambda state. So you don't need to use weights to force that sampling. It does have a lower exchange rate because you need to worry about the energies of two different states in each switch. You can do more switches at a time. That's more complex. There's lots of bells and whistles you could add on to either of these, salsa or guacamole, whatever. But you need to run in replicas though if you do this. And so you need to have, if you have 40 different alchemical states, you need to be running 40 simulations in parallel, and they need to communicate quite a lot. If you want to have fast sampling, then they might need to communicate, every multiple times a second, which can cause problems on large clusters, MPI errors falling all over the place. I say two because you could also consider lambda dynamics as doing molecular dynamics in the lambda state rather than Monte Carlo in the lambda state. That's really sort of a sub-version. So there's different ways to sample in the alchemical, to perform your sampling and dynamics in the alchemical. Okay. But the improved sampling in alchemical free energy methods can fail in certain scenarios. You might have a free energy barrier that is present at all alchemical states. There's some torsion in the protein or even the ligand that is present at all times, that's dividing the whole alchemical and lambda space into two separate, dynamically separated subensembles. You could have a free energy basin. Something that we've found is that maybe your intermediate state is really greasy and it ends up sticking to another part of the protein because it's so greasy. So that slowed down the dynamics that way. But then now let's look at some corn tortillas instead of flour tortillas. Alternatively, collective variable methods have been frequently used to accelerate configurational sampling and sample through space. methods that provide some bias along slow collective variables, adaptive biasing force, metadynamics, and its many variations. So the general metadynamics approach is you pick some collective variable and you build up a bias. So if you visit some values of the collective variable, you build up the bias there and you stop visiting those values of the collective variable. That forces the simulation away from the low free energy values of the CV and allows it to, there we go, into other values along the CV and equally sample the CV. There's a lot of convergence issues there to deal with, but this is a way to force things, if you can identify a CV, to force things away from that. Okay, but wait a minute though. We've talked about building up a bias in some variable to force even sampling. Well, we were just talking about this before. So remix one, bass drop now, metadynamics and expanded ensemble combined together. So this is work we've done with Bussi's group, and Weitze, who did a lot of the work, is here in the audience somewhere in my group. Formerly in my group, now at Phil Bacon's group. So lambda metadynamics applies the principles of metadynamics biasing potentials in the alchemical space. So we treat lambda as another collective variable. There's some details. It's a little different than the collective variables, but it turns out the math is the same. You have to interpret it slightly differently, but it's exactly the same math. We carry out the dynamics or Monte Carlo and lambda, and we accumulate the bias using all of the many metadynamics approaches that have been developed, well-tempered metadynamics, etc., and the same code, plumed. So the expanded ensemble becomes metadynamic sampling. So great, we can do that, but the important thing is the higher dimensional cases allow you to sample both alchemical and configurational space at the same time. So then you integrate out the coordinate degrees of freedom to get the free energy, and the alchemical free energies are just the G lambda 1, G0. So this is implemented in the official GROMACS and Plummet code. It needed like about 30 lines of code, and that was it, hooked together because the theories were already so similar. So just as a sanity check, looking at salvation for energy and argon atom, this comparison between the expanded ensemble purely in GROMACS and where plumed was driving all, it wasn't driving the Monte Carlo that was in GROMACS, but it's driving all of the assembly of the potential just using the plumed tools that were already there before we hicked it in. And you can see that the free energies are essentially the same. It's doing the exact same thing. But the key thing is coupling configurational lambda sampling. So here the task, salvation for energy calculation of a model with charged interaction sites. So because there's charges on this, then these two configurations have different salvation free energies because they have different dipoles. And this torsion, we add a large torsional barrier, like 50 kT. So it looks like the free energy looks like this in alchemical space and in our collective variable space. Right now, it's just a very simple torsion. And if you run simulations starting from state A or state B, you get no sampling of the other state, right? There's this big torsional barrier, and the free energy of salvation is completely different between these two. But if you then do 2D metadynamics in lambda and your torsion collective variable, you accumulate this 2D bias that flattens out the entire free energy surface. That's what the free energy surface looks like now. And this is what sampling looks like, regardless if you start in A or B. And now the free energies you get are independent of the state you start in. So this is sort of the simplest possible example, but with all the work that's been in metadynamics to identify configuration space, you just collective variables that are slow, you just add on the alchemical variable as an extra variable and then do the exact same thing, integrate out and get your free energies at the end. So we've applied this to some interesting free energy calculations looking at the anti-Ensen methylation of adenosine and the difference in solution and in duplex. This is a very slow process that you can't just run the alchemical simulation for. But if you go through, we did a number of Hamiltonian replica exchange simulations. Do this, but these can be replaced by 2D alchemical metadynamics, and what you get is the results are sort of exactly the same. But additionally, you get the torsional free energy profile that you didn't get with the previous calculation. So this is just one example of how these can be used, and I look forward to seeing other ways that people can combine these together. So that's the first combination there. And yeah, so many possible, anything you can think of with slow CVs, if there's a way to accelerate that with some metadynamics or similar approaches, you just combine that with free energy perturbation. That's the first remix. Remix 2, expanded ensemble and replica exchange. So this is work done by Waitsy and also Annika Friedman in my group, who isn't here over the last year or so. So Hamiltonian replica exchange requires n replicas to sample n auxiliary states, and this can be very restrictive. Let's say we're running Hamiltonian replica exchange on a 128 node. It's pretty easy to, if you have 2 replicas, 4 replicas, to figure out how to allocate processes between the number of states that you have to run and how many cores per state. So if 64 states are insufficient, next logical number is 128. You're leaving out these cores here and there. It gets sort of messy. Yeah, you can run multiple replicas per core, but there's still issues. There's a lot of communications issues, a lot of planning issues. So we thought of this idea of combining Hamiltonian replica exchange with a replica exchange of expanded ensemble. So in Hamiltonian replica exchange, you've got 1 lambda per MD trajectory. Those switch. But with REXEE, you've got multiple lambda states. Each of them is running an expanded ensemble state that covers some of the lambda states. So, and you overlap them so that you can exchange them if they happen to be on compatible lambda states. And it can either be done that they only switch when they're on the same, or they can do a Boltzmann weighted switch off on slightly different lambdas. They can exchange, and now instead of this number that you need a smaller number of runners in order to sample the entire range of lambda states. Yeah, so and each of these individual ones are swapping between a narrower range of lambda states, but the overall process covers the entire grid of spaces. So we're just decoupling the connections between the states that are visited and the replicas. You can do exchange for between 0.6, 0.8, 1.0 at the tens of time steps, and then swap between them more globally. So you don't need cores at very low latency. These swaps can be happening at 30 seconds or so, and a much more flexible allocation of cores between parallel MD and replica states. 300 states on 4 replicas. However you want to divide them up. It also improves the convergences of the biases for expanded ensemble because you can converge them locally rather than like missing a whole chunk of lambda space. You're guaranteed that you're getting visits in each interval of lambda space. And this allows you really to run some topologies with arbitrary numbers. 2-dimensional grids, you can U-shaped grids, 1-dimensional grids, you can decompose them any way you want to have little chunks that are locally visited, within simulation expanded ensemble, and then between runners exchange there. So this might be particularly useful when you're doing some sort of 3D replica exchange where you have 3,000 states. We don't have 3,000 computers, but who cares? You can run it on 100 computers, each of which is sampling 30 states. So, I mean, and we've done a lot of just sort of testing to see how this works out. Obviously, higher swapping efficiencies leads to higher sampling efficiency in the alchemical state. If you sample too slow, every 50,000 steps, your state correlation index, how long it takes really to go all the way up and down the chain is, oops, did the same mistake that everyone else is doing. There we go. All right. But once you get down to swapping every several thousand steps, you essentially decorrelate in state space as fast as expanded ensemble, which is slightly faster than replica exchange. A higher overlap leads to higher sampling efficiency. There's ways you can play around with it, but there's some sampling efficiency difference. Same answer regardless. It's just different ways to decompose that problem. There's one interesting thing that took us a long time that we don't entirely understand is one interesting thing is if you're running replica exchange, you notice that with these biasing weights, like the biasing, you have the weight between state 2 and state 3 that occurs in multiple simulations. You could ask, how can you best use all of this weight information? Maybe like averaging it or whatever, but it turns out that the short answer is no. averaging weights between these and sort of adaptively combining these always seems to make it worse. So I won't go into all the details there. So there's some very subtle stuff going on, but there are some things that might seem obvious to do that won't work there. Actually, the simplest thing is you just let each of them have their own weight and then combine at the end. What about exchanges between different chemical systems? We talked about exchanges along the same alchemical direction, but one thing we've been playing with as well is exchanges. So each expanded ensemble simulation might be doing one alchemical transformation, but could you have different alchemical transformations on the different replicas? For example, and so this is the multiple topology replica exchange to leverage conformational sampling from multiple transformations. So test case, say we're interested in some problem where we're going to grow a chain. And so each replica has a different length of chain. And then we do accepts and rejects at the end. You set this up so that the potential energy is the same at each end state. The lambda equals 1 end state of here, and the lambda equals 0 end state of here. And so you can run those as exchange. You do the exchange. You line them up. You have dummy atoms that you build in the missing coordinates for missing atoms there. And you do them entirely in the dummy state, so it's accepted regardless. And you end up with them exchanging configuration. And then continue that. And so you're sharing the example. So this is multi-topology REXEE or Mount REXEE. The TRX is now on the mountain. It's demonstrated. And so we can run a full ligand transformation networks with this. MUP1 system. There's, doing it different ways. Replica, doing the multi-topology versus standard replica exchange. We get all the same answers within numbers. And the round trip time to go over all of these. If you're exchanging every couple thousand steps, which this is about every 30 seconds or so, and the teardown buildup is about 5% of the time, and 95% of the time is building. So it really doesn't cost that much to do this. You get full movement through this ensemble in the order of nanoseconds. A cool flexible binding system we're looking at. We're exploring with collaborators the binding selectivity of fatty acid synthases. They act in a range of alkyl chains. They're really interested in seeing how these are these enzymes are differently sensitive to different length alkyl chains. And so we build a system where we're growing in and out the fatty acid and to look at all of the binding affinities of all of them simultaneously. And so just like a movie of what's going on is you have the chain growing in, shrinking in, and then growing back out. There's these two pockets that do not interconvert on the hundreds of on the microsecond time scale. But doing this, we can grow the pocket in and out, and it grows in and out and visits each of those pockets. So if you started in pocket A, pocket B occupancy with MD, as the length grows, it just doesn't visit it. But with Mount REXEE, it visits both pockets. And you can converge the free energy difference and look at, hey, if I make a mutation, how do I change the sensitivity to the binding free energy as you go through? So we can see how the different mutations are affecting the binding free energy, how when we make this mutation, we destabilize B and shift it more towards A. So and the convergent within statistical error in 100 nanoseconds for each of the replicas, where with 100 nanoseconds would never get it to visit between. So you might say, wait a minute, I've read some Charlie Brooks and now Jonah Vilsack papers. Isn't this kind of like multi-state lambda dynamics? And the answer is yes. But the difference is we're moving the complexity out of the MD code and into the pre-processing. So these are all running on GROMEX with 0 modifications. All of the exchanges and stuff are done outside. Multi-state lambda dynamics is more efficient since it's only simulating one copy of the protein. But REXEE is giving you a better sampling of the proteins because you're simulating 20 copies of the protein. So it's not just one protein that is looking at the 20 ligands. You've got 20 proteins that can individually sample, but then the ligand gets to look at each of those 20 protein samplings and lower complexity of coding. You don't have to redo the inner loops of the force calculations to get this to work. It also can be used to drive grand canonical Monte Carlo simulations. We're working on that and inserting molecules one by one into a system. And really look forward to improvements coming from comparing, contrasting, combining. Like, what is the gordita you stick inside the quesadilla? We really want to see from this. So yeah, future work, how can we really combine these to ligand maps and explore, from the beginning, setting up, tens of thousands of ligands, and then gradually use machine learning to decide where you're going to go as you move through space with large ensembles of these ligands running. So yeah. So conclusions. It's important to really sit down and think and deconstruct enhanced sampling methods to understand the components and how they relate. If you understand the components and how they fit together, you can really start remixing them in ways that have real advantages. We can combine metadynamics with expanded ensemble methods to simultaneously explore configurational alchemical CVs. We can decouple replicas from states with REXEE. Hire Annika Friedman. She just graduated. She did all the Mount-REXEE stuff as well as the fatty acid stuff and a bunch of other papers. So she's really good. The maple snickerdoodles show up in the lab all the time. So she is a great teammate. And come talk to me if you have a position because you won't regret it. Check out our papers and tutorials. A bunch of the links to the papers there. Just go to the QR code as well as all. Thanks very much.
Thanks, Michael, for the great talk. So we have time for one question. Let's thank Michael again. Thanks so much.